Assalamualaikum warahmatullahi wabarakatuh. Now we continue our chapter 3 on part B, is specific energy and control station. Okay, so we just continue that example here, activity 3.9 here. Okay, a rectangular channel conveys flow at y naught is equal to 1.6 meter and r is equal to 0.77 meter on s naught 1 over 3000 and meaning n is equal to 0.01. Okay, so what is the minimum height of gear to control the flow in the channel? Okay, so this is based on the previous slide, based on part A. Okay, calculate depth of flow upstream, downstream and above the weir in A here. Okay, and calculate depth of flow upstream, downstream and above the weir if the height of weir is 0.4 meter and 0.6 meter. Okay, so this is the example using the rectangular channel. Okay, so we know that the given data is y naught is 1.6 meter. Okay, r is equal to 0.77, s naught is 1 over 3000 and n is 0.01. Okay, we know that the y naught is 1.6 meter. Okay, using this equation for rectangular channel, okay, you use this one because we know that the q, okay, the small q, this discharge per meters width is based on the b here. Okay, so we use this formula, okay, to get the discharge per meter width. Okay, so because we don't know the discharge, okay, the value of discharge, so we want to find the discharge per unit weight. Okay, so you just put the value here. Okay, and the y naught is 1.6 meter here and the r is 0.77 here and the s naught here, and until you get the value of q, discharge per meter q, discharge per second, okay, discharge per meter width. Okay, so we get the value of 2.454 meter cube per second per meter. Okay, so discharge per width. Okay, so now you use the YC, the formula of YC to get the YC based on rectangular channel. So, and put all the value here until you get the value of 0.8499 meter. Okay, so don't get the YC. Okay, so we know that the Y naught is 1.6 and YC is 0.8499 meter. So we know that the Y naught is more than YC. So this is the subcritical flow. So they have the step by step. Okay, the step 1, okay, and then step 2. Okay, step 2, calculate H minimum. Okay, calculate H minimum based on the specific energy formula. Okay, you just put the value here until you get the value of E naught is 1.720 meter. Okay, and we know that the E minimum is 3 divided by 2 times by the YC formula here. So you just put the value and we get the E minimum is 1.275. Okay, so you get the value of E minimum. Okay, 1.275. So we know that the H minimum is E naught, E normal minus by E minimum. So we get the 0.445 meter. So then step 3 to determine Y1, Y2 and Y3. Okay, so in A, we know that H is equal to H minimum. Okay, H minimum is 0.445. Okay, and we know that the H is in case 2, H is equal to H minimum is in case 2. So for case 2, so Y1 is equal to Y3 is equal to Y naught. Okay, is equal to 1.6 meter. Okay, so Y2 Y2 is equal to YC is equal to 0.8499 meter. So we know that this is the value because we know that in AH is equal to H minimum. Okay, So now we look at the calculation for C. Okay, if H is 0.4 meter, so this is less than H minimum. Okay, so H minimum is 0.445 meter. So this is in case 1. Okay, so you must know that which is the case 1 and which is the case 2. Okay, so now for case 1, y1 is equal to y3 is equal to y0 is equal to 1.6 meter. Okay, and then E2 is E0 minus by H minimum. So H, so we get the value of 1.32 meter. Okay, so now based on the specific energy equation, you just use the Y2 here, okay, and just put the value until you get the E2 here, 1.32, okay. So, and then using the try and error method, so you get the Y2. Okay, the Y2 with 1.032 and or Y2 is also at the 0.7085 meter. So you get the value here. Okay, maybe you can using the graphical method. Okay, graphically method, or you want using the trial and error. Okay, so you get the value of this one and also this one. Okay, so since y0 is subcritical, so y0 is subcritical with, so we get the y0 more than yc, y2 more than yc, so the y2 is 1.032 meter. Okay, based on, if you get the y2 is 2 value, okay, but you must using that y0 is subcritical here, okay, based on the y0 is 1.6 here, okay, so that's the mass. Y0 is mass more than y2 and mass less than yc here, so we get the value of y2. Okay, this is the concept calculation step by step. Okay, now to find the h, if h is equal to 0.6 meter, so the h more than h minimum, so is equal to 0.445 meter. So this is in case 3, backwaters. Okay, so in case, so for case 3, so y2 is equal to yc. Okay, so you get the 0.8499. So no need to worry about this is more step by step. Okay, so our test or our final is just only find until at the A. Okay, not to B or C. Okay, and that's all, so you no need to worry. Okay, this is just for your calculation, for your knowledge how step by step to find the value. Okay, to for case 3, so y2 is equal to yc here. Okay, and you get the 0.8499. Okay, so and to get the E at the 1, okay, and at the 3, okay, y1 and y3, okay, so we get the minimum E minimum based on this calculation here and this formula here, using this formula for case 3. Okay, this is referred to the table. Okay, and you just put the value until you get the 1.875 meter for y, value of y. Okay, then through try and error, okay, based on 1.857, okay, based on try and error, you get the y and the y3 here at based on try and error. Okay, so you just try and error method, so you get the value of this one, and since y1 power more than y0 and the 3 is less than yc, so we get the value here based on the try and error method here. Okay, based on this value, okay, based on this we get the value of this case 3. Okay, that's all. So if you have any questions, so we can discuss again in our tutorial class. Okay, no need to worry about this calculation. So now we look at the flow through constricted channel. So after we learn in part A that flow through broad wasted weir and also the calculation of critical depth, so now we look at the flow through constricted channel. Okay, so if width of a prismatic channel okay, is reduced or enlarged at a section. This is reduced here or enlarged here at the channel here. So uniform flow change to non-uniform flow. Okay, change to the water surface profile is influenced by the width of constriction B2 and the constriction B2 here, and the flow condition before the constriction, either supercritical or subcritical here. Okay, the condition of at A and at 2 and also at 3 here. Okay, and bed elevation at 1 and 2 are the same. 1 and 2 are the same here. E1 is equal to E2. Okay, so this is the from this plane view here. So this is the side view. Okay, so since B2 is less than B normal, Q2 is more than Q normal here. So we use this formula for specific energy. Okay, based on the channel. Okay, based on the rectangular channel here. Okay, based on the all section channel or rectangular channel. So you can use this equation based on the constricted channel. Okay, maximum. So this is the concept. The maximum width of constriction be max. So when the broad waisted weir is using the H, okay, H minimum and H, okay, H and H minimum. For constriction, we use the B maximum, okay, B or B maximum. So width of constriction B2 determines the depth of flow at the constricted section Y2, okay, where the Y2 is equal to Y critical at 2 or not. Okay, so the B maximum is the maximum width of constriction which still start to produce critical flow depth at the constriction. So Y2 start to change to Y critical at 2. Okay, so Y critical at normal here or Y critical at 1. Okay, critical depth of flow along the unconstricted section. Okay, so YC2 is critical depth of flow at the constricted section. Okay, so generally depth of flow at constriction Y2 is B2 more than B maximum. So the Y2 is not same as the Y critical at 2. Okay, so B2 is equal to B maximum. So the Y2 is equal to Y critical at 2. Okay, so B2 is less than B max. So Y2 is equal to Y at C2 more than YC2 here. Okay, so you must this based on this basic assumption here. Okay, so therefore Y2 is equal to Y critical 2 or Y power of C2 here, and E2 is E minimum if B2 less and equal to B maximum. So based on this part here. Okay, so this is the based on, so we can see this figure. So we just look at this figure here. Okay, so this is more clear based based on from this figure. So just clear to this figure. They also have the case 1 and case 2 and the case 3 here. So the condition of upstream flow Y naught here. So this is based on the Y naught. Okay, and the subcritical Y naught more than Y critical normal here. Supercritical is Y naught is less than Y C naught here. Okay, so this is based on this case 1, case 2 and the case 3. Now step in analyzing flow through constriction. So this is based on step by step. Also same as the step in broad crested weir. So now we have the step in constriction. Okay, so calculate Y naught and Y C naught here. So you must calculate Y naught and Y C naught. Okay, the in broad crested weir. So you must find the Y naught and also YC. Okay, so this is on constriction. So actually C is the constriction. So calculate the Y naught and the Y critical at constriction. So this is based on the YC. Okay, so determine state of upstream flow Y naught, either subcritical or supercritical, by comparing with the Y critical at Y naught at constriction. Okay, Y critical at the constrictions here. Okay, so if Y naught is more than Y critical at constriction, subcritical upstream. Okay, Y naught less than Y critical okay, at constriction is supercritical upstream. Okay, so calculate Y constriction at 2 Q max and the B max. So when width of a channel is being constricted, Y is constricted 2, can be obtained since E minimum is equal to E naught here. Okay, so once B max is calculated, the condition of flow through the constriction can be established based on B2 more than B maximum is case 1. Okay, so B2 is equal to B maximum is case 2. Okay, B2 less than B max is case 3. And then at step 3, you must find the Y1, Y2, and Y3. Okay, that's all. For their step by step, they have 3 steps. Okay, also same as the 3 step in broad crested wheel. So now we look at the constriction. Okay, so in case 1 here, B2 more than B maximum here. Okay, so this is the subcritical upstream when the Y naught is more than Y critical constriction. Okay, so this is Y naught. Okay, this is Y critical. Okay, Y naught as the constriction here. Okay, so and the YC at the critical here. Okay, 2, and this is Y2. Okay, and supercritical here, Y naught here. Okay, less than YC naught here. YC naught is the Y at normal constriction. Okay, before the constriction, so the normal here. Okay, so Y naught is less than Y2 is less than YC2 here. YC2 is at the constriction here. Okay, this is based on the figure here. E naught is equal to E1 equal to E2 and equal to E3. This is based on the subcritical upstream. Okay, and supercritical upstream, so we know that E naught is equal to E1 is equal to E2 in E3. So there's the same here, and to get the E minimum, and E minimum at O normal here. Okay, at the CO, so we get the CO here and the C2 here. Okay, so for case 1, so step by step use all the value. Okay, useful equation is based on the rectangular or all section here, so you can use this for all section, or you can use also for the rectangular. So this is for all section and the rectangular. Okay, so calculate Y2 at Y is critical at 2 and Q max and the B max here. So you use based on this equation here. Okay, so based on the specific energy equation, okay, based on the E minimum equation for the rectangular, this is for the also rectangular, also use, or you can also all section. Okay, or this one, so you can use for the this one. Okay, maybe you can use the for the rectangular. Okay, for this equation, actually for this rectangular. Okay, so now look at the determine y1, y2, and y3. You use this equation. This is the basic assumption for case 1. Okay, for the case 2, B2 is equal to B max. So we know that Y naught is more than YC naught here. Okay, so and supercritical upstream is Y naught is less than YC naught here. So this is based on the case 2. So the case 2 step by step is also the same equation here. Okay, same the equation for step by step here, but the value for y1 and y2 is the difference based on the case 1. Okay, so the other same, the other to get the y naught and y not at the y critical at constriction. Okay, so we get using this equation, and second calculate also the same formula, and they determine y1, y2, and y3 based on this formula. Okay, for the case 3, B2 less than B max, so based on this figure here. Okay, Y naught more than YC naught, and supercritical Y naught is less than YC naught, so we get the case 3. So the calculation also with the same equation. Okay, for the difference is based on Y1, Y2, and Y3. So this is the equation, so no need to worry. All the formula is given. Okay, not to worry. Okay, maybe the formula is given as randomly. Okay, so you can choose from that list of formula. Okay, so now look at the activity 3.7 here. Okay, the bridge is to build across a 50 meter wide rectangular channel. Okay, carrying flow of 200 meter cube per second at depth 4 meter. So for reducing the span of the bridge, what is the minimum width of channel such that the upstream water level will not be influenced by the constriction? Okay, the given data is Q, okay, 200 meter cube per second, and the Y naught is 4 meter, and the B is 50 meter. Okay, so determine Y naught and YC naught, okay, to get the critical. Actually, YC naught is critical at constriction, okay. So the Y critical at constriction here. So Y naught, we know that the 4 meter, okay. To get the Q naught here at the normal, Q at the normal with the Q discharge divided by the B here. So we get the 4 meter cube per second per meter. Okay, so you get the value here. Okay, and then to get the critical, Y critical for constriction, so we just put the Y critical for constriction using this equation. So we get the 1.177. Okay, so we know that the Y naught, okay, 4 meter, and the Y critical at constriction is 1.177. Okay, so this is less. So Y naught is more than YC naught here. So this is the subcritical. Okay. So YC is influenced by Q. When Q change, YC varies as well. Therefore, at constriction, where Q is not the discharge per width is not based on Q naught here. Okay, so calculated in step 2. Okay, so now we look at the step 2. Calculate YC2 and B max. Okay, to E naught using the specific energy formula. Okay, you just put the value here and until you get the 4.51051. Okay, and then at width B maximum, E2 is equal to E minimum. Okay, and Q is Q max equal to Q max. Okay, so with no energy losses, so E minimum is equal to E naught. Okay, so based on the therefore, so to get the YC critical at 2, okay, so we get 2 over 3 here, okay, and is equal times by the E minimum, so we get the value of E minimum is actually this one. E minimum is equal to E naught. Okay, so we get the value of 2.701. Okay, so this is the step by step to get the Y critical at 2 and the B maximum. Okay, so after you get the YC2 here, so you get the to get the Q maximum here. Okay, using this formula to get the Q maximum, so you get the Q maximum is 13.90 meter cube per second, sorry, meter squared per second. Okay, so you get the actually Q max is meter cube per second per meter. Okay, you just put here, so you get the meter squared per second. Okay, that's why you get this one. Okay, so now you get the Q max is Q discharge divided by the B max here. So we know that the B max is 14.39 meter here. Okay, so the step by step. Now we look at the step. Okay, after you get the step 2 here. Okay, and then you look, because the question is just to get the water level will not be influenced. So for the span, what is the minimum weight? So minimum weight is B. We get the B max here. Okay, so B max until you get the B max. So now we look at the example activity 3.8. Okay, so actually this is similar to the solution in activity 3.7. Okay, actually it's 3.7, similar to the activity of 3.7. Okay, the activity 0.8, this is activity 0.7. Okay, so activity 0.7, you get the same. Okay, because the Q naught is 4 meter. Okay, you get the Q naught is the same. Is it the same? Okay, the same here. Okay, just step by step here. This is same as 3.7. Okay, So a bridge is to be built across this one. So just the step by step. So just calculate based on similar to the solution in activity 3.7. So you get the Q naught is 4 meter here. So and we get the C naught here. Okay. Critical depth at the constriction is you get 1.177. So Y naught is subcritical flow. Okay. So this is to determine the depth of flow upstream, downstream, and under the bridge. Okay. So now we use the calculate OIC here as the same 3.7. Okay. So use the same here. So you get the value and also this one. Okay. And we get the YC naught here as the 2.701. Okay. And we get the value of Q max. Okay. That and just add the step 3. Okay. So this is just add the step 3 because you want to get the upstream. Okay. Because you want to get the upstream, downstream. Okay. Upstream, downstream, and under the bridge. That's why you must calculate until to step 3. Okay. So this is based on the question. Okay. So this is for step 3 to get the Y1, Y2, and the Y3 here. Okay. So since B2 is equal to 30 meter and more than B maximum here. Okay, so we let's case 1 here. So E2 is equal to E naught is this equation, is this value. So we calculate using this specific energy, okay, based on the Y2 in using the this E2 here, based on the E2 here. Okay, and you use the try and error method, okay, to get these two value here. Okay, since Y naught more than Y C naught here and YC2 is less than Y2 and less than Y naught, so the Y2 is this one. Okay, so this is the concept. Okay, so you must read properly your question. Okay, if they want to find the upstream, okay, downstream, and under the bridge, same as until at the step 3. If not, we just stop until at step 2. Okay, that is the difference. Okay, the different case based on the activity 3.7 and activity 3.8. Okay, now we look at the activity 3.9 here, the example here. Still using the rectangular channel, okay, with okay, is required to convey 3 meter cube per second. So to find the determine the width of the maximum constriction, okay, to find the B maximum for critical depth and calculate the depth of flow upstream. Okay, so flow upstream, downstream, and the constriction if the constrict with 1.2 meter. So must calculate until step 3 because the flow upstream, downstream, and constriction here. So you must calculate until step 3. So now use the step 1. Determine Y naught and Y critical at constriction. So we get the Y naught here and we get the Y critical not here. Okay. So since Y naught is more than Y C naught here, so we get the subcritical flow. Okay. Now using the step 2, okay, to find the critical at 2 and B maximum. Okay. Using the specific energy formula, just put the value here until you get the 0.9792. Okay. So and we get the Y critical at 2, 2 over 3 E minimum. So we get the value of 0.6528 meter. Okay. So and then after you get the YC here, YC2 here, so you must find the Q max. Okay. Q max, so you get the 1.652 meter squared per second. Okay. So and then to get the B max, so we get the value, just put all the value. Okay. So now look at the step 3 because the give you to B2 is 1.2 meters. So you know that B2 is less than B max. So B max is 1.816. Okay. So B2 is less than 1.816. Okay. So we get that value. Okay, we get that value. Okay, and case 3 where new Qmax is required. Okay. Okay, now calculate set 3 here, calculate Y1, Y2, and Y3. Okay, so Q over max here. So Q divided by the B2 here, because the B2 is 1.2, so you get the 2.5 meters squared per second. Okay, and Y2 is equal to Y critical at 2 here, so you get this value. And then E minimum, so you get this value, just put the value. And lastly, you use the E1 here, because this is the step 3, so you must find the value here and put all the value here until you get the here 1.291, and you get the two value of Y1 and Y3. Okay, that is the step by step until to step 3. Okay, now look at the activity 3.10 here. It's also the rectangular channel. Okay, so the step 1, because this is to flow upstream, does not change, so you just until to step 1 is okay, just use find the Y naught and Y critical at constriction, so you get the value here. Okay, and we get the subcritical flow. Okay, so and use the step 2 here to get the H minimum. Okay, H minimum is E naught or E minimum, so you get the determine Y1 and Y2 and just put all the value until you get here. Okay, and this is just sketch. Now we look at the activity 3.11. Okay, so a rectangular channel, still also use the rectangular channel. Okay, because this constriction. Okay, so just remember that for constriction, so we just use the rectangular channel. Okay, so calculate the depth of flow upstream and downstream, so we just until the step 3. Okay, actually for this also at the sketch here. Okay, before we just step 2 and step 3, so you sketch and just look at this one 3 point. So any questions, so we can discuss again in our tutorial. Okay, no need to worry. Okay, I just go through for this slide. Okay, based on this lecture class, so we just go through. Okay, and any question or any discussion, so we can discuss in our tutorial class. Okay, now we look at the activity 3.11 here. Okay, to get the rectangular channel. Okay, because it must include the sketch. Okay, so this is based on the include based on the sketch of constriction. Okay, so given here, given the data here, and first you must find the Y0 and YC0. Okay, so using the, because this is not given the Y0. Okay, so they'll just give you the B and B2 here and no Y0. So that's why you must find the Y0 first. Okay, find the Y0 using this equation. Okay, so you must refer to the topic 2. Okay, sorry, chapter 2 to get the normal depth. Okay, so to get the normal depth based on the try and error, so you get the value of normal depth is 2.270. Okay, so you get the value of Y0. Okay, based on try and error. Okay, now after you get the Y0, so you must find the YC0 here. Okay, Y critical at constriction. Okay, so you get the value, put all the value, and we get the 1.131 meter. Okay, so since Y0 is more than Y0, it is subcritical flow. Okay, so now use this calculate step 2. Okay, to get the Y critical at 2 and the B maximum. So use the energy specific energy equation formula here, so just put the value until you get the value of 2.411. so no need to worry, because all the equation, specific energy equation or critical equation is given to you. Okay, no need to worry. Okay, you must know how to use that formula. Okay, so now for the step 2, so find the E naught here. Okay, the Bmax is when Q is equal to Q max, where E minimum is equal to E naught here. Okay, so you get the Y critical at 2 based on this formula. Okay, and you get the value of 1.607. Okay, now we look at the Qmax here. Okay, when you get the value, you just put the value of Qmax here. Okay, 6.381 meter cube per second. Okay, so then Bmax, so we get the Q divided by Qmax here, so we get the value here. Okay, so we get the value. Okay, so the 1.536. Okay, so you get the value, and this value here and the value here. Okay, so you get when B2 is 2.4 meters, so we get the B2 is more than Bmax. So we calculate using the step 3 because you want to find the upstream and downstream. Okay, so that's why you must calculate. So this is in case 1. So E minimum less than E0. So E2 is equal to E0. So the calculate Y1, Y2 and Y3 using the step 3. Okay, so Y1 is equal to Y3 is equal to Y0. So we get the value of 2.270. Okay, based on the Y0 that you get from the previous slide. Okay, so you find the Q2. Okay, and the value of this one, and we get the YC knots. Okay, at the so we get this one. Okay, and then you must catch. Okay, after you get all the value that you find from the previous slide, so you must catch here. You must catch that you get the Y naught. Okay, you must catch the E naught, YC naught, and so on. Okay, then you get the using the specific energy for at critical at 2. Okay, so you use the Y2 here until you get the Y2 using try and error. So you get the Y2 is 2.242 and Y2 is 0.7059. Okay, since it's subcritical upstream, okay, subcritical upstream, so we get the Y2 is 2.242. Okay, so you now you sketch. Okay, so this is my sketch based on the value you get. Okay, Y2, okay, and the Y0 and YC0 and E0 and E2. Okay, so you just sketch here. So you sketch, you get the 2 marks. Okay, so at the calculation, so you get 1 mark until you get the. So this question is 10 marks, 8 to 10 marks. Okay, so the maybe the 8 mark for the calculation and 2 marks for the sketch here. Okay, so this is the concept for constriction based on step by step. Okay, so now look at the choking here. Choking of flow occurs when H is more than H minimum, okay, of broad crested weir in open channel. Okay, so B2 less than B max at the constricted width in an open channel. So this is based on the choking of flow. Okay, choking of flow occurs when these two step here. Okay, based on broad crested weir and also the constricted open channel. So when the specific energy of depth of flow immediately upstream, okay, of the weir or constriction increase or being controlled. Okay, so choke conditions are undesirable in the design of covered and other surface drainage features involving channel transitions. That's all for this is the choking. Now this is the assignment and tutorial. Okay, so we just look here. Okay, and then that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Then we can discuss again more on the critical depth. Okay, and based on the broad waisted weir and the constricted we are okay constricted so channel, so we just discuss again in our tutorial class. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.